In this lecture, I'm going to continue to talk about the stress energy momentum tensor. And remember, that's the tensor that sits on the right-hand side of the Einstein equations. So the Einstein equation is g mu nu equals 8 pi times Newton's constant over the speed of light to the fourth power times t mu nu. So the left-hand side is the Einstein tensor. On the right-hand side, we have the stress energy momentum tensor. The stress energy momentum tensor contains all the information about the stresses, energy, and momentum of the matter fields or non-gravitational fields. The left-hand side of the Einstein equation is, of course, the Einstein tensor, which is constructed from the metric and derivatives of the metric. So this is a set of differential equations that determine what the metric is for a given matter distribution. In other words, for a given stress energy momentum tensor. One question you might have is, where does the stress energy momentum tensor come from? One possible answer is from a variational principle. Let me give you an example. Let's look at the electromagnetic field. We define the field strength tensor F mu nu as del mu A nu minus del nu A mu, where A is the 4 potential. And if you expand these covariant derivatives out into ordinary derivatives and Christoffel symbols, you'll see that the Christoffel symbol terms cancel between these two terms. So this is the same thing as partial mu A nu minus partial nu A mu. Now the action for the electromagnetic field is a functional of the potential A and the metric, and it's equal to minus 1/4 square root of epsilon naught over mu naught. That's the permittivity of free space and permeability of free space, times the integral over spacetime d4x times the volume element square root of minus g times F mu nu F mu nu. Notice that the metric appears in this action not only as in the square root of minus g here, but also we've had to raise the indices on this F mu nu using the metric. So this is actually F alpha beta G alpha mu G beta nu times F mu nu. And F mu nu itself, written this way, doesn't depend on the metric at all. So the metric appears here and here. Now we can vary this action, or extremize it. The action depends on two fields, A and G. So the result, through the usual procedure that should be familiar, we put this into the form of something times the variation of A plus something times the variation of G mu nu. And just by way of notation, this coefficient here is referred to as the functional derivative of S with respect to A, and denoted this way. This is the functional derivative of the action with respect to the metric, denoted this way. Now if we extremize the action with respect to A, so in other words, we set the functional derivative of S with respect to A equal to 0, what we get is Maxwell's equations. Well, more precisely, 2 of the 4 Maxwell equations are automatically satisfied by writing the field strength tensor in terms of the potential this way. But the other 2 Maxwell equations come from extremizing the action with respect to the potential. What about this functional derivative? Well, the functional derivative of the matter action with respect to the metric defines the stress energy momentum tensor. And here's the definition. T mu nu is equal to 2 times the speed of light over the square root of minus g times the functional derivative of the matter action with respect to g mu nu. So this is a general definition true for any matter fields. For the electromagnetic field in particular, this definition gives us T mu nu equals 1 over mu naught times F mu alpha F nu beta G alpha beta minus 1/4 F alpha beta F alpha beta G mu nu. Notice I haven't extremized the action with respect to the metric. That's because this isn't the complete action. This is only the action for the electromagnetic field. So let me put a little EM for electromagnetic field here. And now this definition holds for any matter field, so I'll put a little subscript matter onto this S. And this was then the stress energy tensor, of course, for the electromagnetic field. Now the complete action is the action for the gravitational field. It's called the Einstein Hilbert action, so let me put a little subscript EH, plus the action for the matter fields. So each EH stands for Einstein Hilbert. So I'm not going to discuss the Einstein Hilbert action now. I'll save that for a later lecture. But let me just state that the functional derivative of the Einstein Hilbert action with respect to the metric is equal to minus c cubed times the square root of minus g divided by 16 pi times Newton's constant big G times the Einstein tensor. Right? And now couple that with the fact that the variation of the matter field with respect to the metric is, as we saw above, square root of minus g over 2c times the stress energy momentum tensor. So now if we extremize this action with respect to the metric, what we have is the functional derivative of the Einstein Hilbert action plus the functional derivative of the matter action equals 0, and that gives the Einstein equation. G mu nu equals 8 pi g over c to the 4th times T mu nu. So as I said, I'll discuss all this in more detail in a later lecture, but this gives you an idea of where the stress energy momentum tensor comes from. It comes from the functional derivative of the matter action with respect to the metric. And one thing you'll notice about this definition is because the metric is symmetric, the stress energy momentum tensor must be a symmetric tensor. And of course, you could notice that directly from the Einstein equation. Since G mu nu, as we've seen, is a symmetric tensor, T mu nu must also be a symmetric tensor. In the last lecture, I gave a detailed interpretation of the stress energy momentum tensor for an observer with 4 velocity u, and the observer carries basis vectors E1, E2, and E3, and these define the spatial directions for this observer. These vectors are orthogonal to each other, they're normalized, and they're orthogonal to the 4 velocity u. So for this observer, the energy density is 1 over c squared T mu nu u mu u nu. The momentum density, or the density of the ith component of momentum, let's call that I momentum density, is minus 1 over c squared, t mu nu, e mu I u nu. The energy flux in the ith direction, the direction of the ith basis vector, is equal to minus t mu nu times u mu e nu I. And finally, the j momentum flux, so this is the flux of the jth component of momentum, in the I direction, is just equal to t mu nu e mu I e nu j. Now the observer can construct Fermi normal coordinates in a neighborhood of this world line. So the Fermi normal coordinates we called x bar mu. So the tensor components in these coordinates have bars on them. The energy density then is t bar 0, 0. The I momentum density is minus 1 over c times t bar I 0. The energy flux is minus c times t bar 0I, and the j momentum flux is t bar ij. Remember, the metric in Fermi normal coordinates is just a Minkowski metric, minus 1, 1, 1, 1 down the diagonals. So we can raise and lower these indices in Fermi normal coordinates just with the possibility of a minus sign. So for example, if we raise this 0 index, we get an extra minus sign. Raising the I index, the spatial index, doesn't change anything. So this is equal to 1 over c times t bar I0. And similarly here, raising the 0 index picks up a minus sign, so this is plus c times t bar 0I. We can raise these indices for free, so to speak. And when we raise these two indices, we get two different minus signs that cancel. So this is equal to t bar upper 0, 0. Now, as we saw above, the stress energy momentum tensor is symmetric. And this has several consequences. First, notice that the energy flux in the I direction is just equal to c squared times the density of the ith component of momentum. So how do we understand this result? Well, first of all, remember in relativity, energy and mass are physically the same thing. When we say E equals mc squared, the c squared is just there to change units from, say, kilograms to joules. So physically, this is the same thing as saying c squared times a mass flux in the I direction is equal to c squared times the ith component of momentum density. And of course, the c squareds cancel. So let me draw a picture from the perspective of the observer. So here's a surface that's perpendicular to the ith basis vector. And we have now some mass that's flowing across this surface. And let's say that all of the mass within this region flows across the surface in some time delta t. So here's the mass in this region flowing across this surface. And by the way, when we say the mass flux in the I direction, this is just a shorthand way of saying this is the mass that flows across a surface perpendicular to the ith basis vector. So it's not really a flux in the I direction. It's a flux across a surface perpendicular to the I direction. So in this picture, all mass in this volume, the volume shown here, flows across the surface that has the perpendicular EI. And this is in some time interval delta t as measured by the observer. So if this mass is moving with a velocity v, then the length of this side of the volume is v times delta t. And the cross-sectional area we'll refer to as A. Now the volume of this region, if this is the angle, say theta, then the volume of this region is A times V delta t times the cosine of theta. So now let's return to this relation. The mass flux in the I direction, that's all of the mass in this region, per unit area and per unit time, flows across this surface. And by the way, this is the mass as seen by the observer O, so it's a relativistic mass. It's rest mass times gamma. Right now, from this expression, we see that A times delta t is equal to the volume, as seen by the observer, divided by V times cosine theta. So this is equal to the mass times V times cosine theta divided by the volume. And this is just the ith component, so the cosine theta picks out the ith component of the momentum, the relativistic mass times the velocity as seen by the observer. So this is just the I component of momentum per unit volume. It's the I momentum density. Now let's return to our basic definitions and notice that because T mu nu is symmetric, that implies that the J momentum flux in the I direction is equal to the I momentum flux in the J direction. So how can we understand this? Let me draw a picture. Let's say this is the I direction and this is the J direction. And we have some momentum flowing past the origin. So let me draw some of these flow lines. So we have a bundle of mass or fields that are carrying momentum past the origin. And let's let this angle be theta. And to the observer O, let's say that the observer sees a magnitude of momentum P flowing past the origin. So P is the magnitude of the momentum as seen by the observer flowing past the origin in some time delta t as measured by the observer's clock. And this bundle of flow lines, material or fields, let's say it spans an area A, a cross-sectional area A. So this momentum is spread across area, the cross-sectional area A. Now let's write down the J momentum flux in the I direction. In other words, the j component of the momentum flux across the surface that's perpendicular to the I direction. So the j momentum flux, if p is the total momentum, the jth component is just p times sine of theta. And this is a flux, so it's per unit time, and per unit area, the area of the surface that's perpendicular to the I direction. So that's the area from here to here. And now let me draw a triangle cutting across these momentum vectors this way. We have a triangle whose hypotenuse is the area we're looking for, and this is the angle theta. So this is the side adjacent to that angle. So the hypotenuse is given by the length of this side, which is the cross-sectional area A, divided by the cosine of theta. So here we have the cross-sectional area A divided by the cosine of theta. So the j momentum flux in the I direction is equal to the total magnitude of momentum times sine theta cosine theta divided by delta t times the cross-sectional area A. Now let's compute the I momentum flux in the j direction. The ith component of momentum is p times cosine of theta, and we divide by the time interval delta t and by the area across a surface that's perpendicular to the j direction. So that's the area spanned by these momentum vectors from here to here. And if we complete a triangle whose hypotenuse is the area we're looking for, then this is the angle theta, and the cross-sectional area is the side opposite that angle. So the area is A divided by sine theta. So the I momentum flux in the j direction is equal to P times cosine theta times sine theta divided by delta t times the cross-sectional area A. And of course it's the same as the j momentum flux in the I direction. The next thing I'd like to do is to examine these components of the stress energy momentum tensor from a bit different perspective. So remember, this is T mu nu, E mu I, E nu j. It's the j momentum flux in the I direction. And of course we know that's also the same thing as the I momentum flux in the j direction. So we have a surface that's perpendicular to the I direction, and we have momentum crossing from the left side to the right side. So from the point of view of the right side, the momentum is increasing. So this is equal to the change in momentum on the right-hand side, the jth component, so let me put a little superscript j here, divided by the time interval and the area perpendicular to the I direction. Now, from Newton's second law, we know that the change in momentum over the change in time is just the force. So the change in momentum over the time interval is the force, or in this case the jth component of the force that the left side exerts on the right side. So what we find is that T mu nu, E mu I, E nu j is the jth component of the force divided by the area perpendicular to I. So it's a stress. So let's make sure this is clear. What we're talking about, we have a surface that's perpendicular to the EI direction, and The left side contains matter and fields, and those can exert forces on the matter and fields on the right-hand side. So now these are force vectors. So these are the forces exerted on the right side of the surface by the matter and fields on the left side. And the force can have, of course, any component. It can have components in the I direction. It can also have components in other directions. So the jth component of the force per unit area across this surface is the stress. By the way, the component of the force that's in the same direction as the perpendicular to the surface is referred to as a pressure. So pressure is the name given to the diagonal components of the stress. And the off-diagonal components are referred to as shear stresses. Now, we've already talked about the fact that the stress energy momentum tensor is symmetric. So that means the stress tensor is symmetric. So in particular, the J component of the force per unit area perpendicular to the I direction must equal the I component of the force across an area perpendicular to the J direction. Now, this probably isn't obvious to you. I don't think it's obvious to anyone, but there's a standard argument as to why this should be true that's given in lots of textbooks. And the argument goes something like this. Consider a cube, and there are matter fields inside the cube as well as outside. So the matter and fields in the exterior exert forces on the interior of the cube. Let me draw some of those force vectors. So let's say this is the x direction, this is the y direction, this is the z direction. Then this would be the force that the exterior exerts on the interior, the y component of the force across the face perpendicular to z. And this would be a force in the z direction across a face perpendicular to y. And of course there are forces on the other faces of the cube as well. So the calculation involves adding up all the torques due to these forces on the cube and then let the cube size shrink to 0. So what you find in that limit as the cube size goes to 0 is that the total torque on the cube goes to 0, but it doesn't go to 0 fast enough to keep the angular acceleration from going to infinity. So both the torque as well as the moment of inertia of the cube go to 0 as the size goes to 0, but the torque doesn't go to 0 fast enough unless the torques are balanced. So the torques must balance in such a way as to keep the angular acceleration finite. And that condition of the balancing torques is precisely this condition, that the Ji component of stress is equal to the Ij component of stress. I'd like to spend a few minutes discussing this sudden change in perspective. We have the stress, that's the E mu I, E nu J component of the stress energy momentum tensor. We originally identified this as momentum flux. And now we're referring to it as stress. So the question I'd like to ask is, are these really the same thing? if you remind yourself of how we reinterpreted the momentum flux as a stress, the key to the argument was using Newton's second law in the form force equals time rate of change of momentum. So the question really is the force the same thing as time rate of change of momentum? And I think the answer is no. These are physically distinct concepts, force and rate of change of momentum. If these were precisely the same thing, this would just simply be a definition of, say, a shorthand notation for dp dt. We just call it F. But definitions have no predictive power, and Newton's second law certainly does have predictive power. We can actually solve physics problems using Newton's second law. So I think the answer to this question, is momentum flux the same thing as stress? I think the answer is actually no. So the question arises then, when we are looking at these components of the stress energy momentum tensor, what are we looking at? Are we looking at a momentum flux or a stress? So is E mu I, T mu nu, E nu J a momentum flux? Or is it a stress? And the answer is, it depends. It depends on the type of matter field that we're talking about. The type of non-gravitational field. Let's look at some examples. First example, let's consider dust. If you'll recall, the stress energy momentum tensor for dust is just the mass density times the forward velocity of the dust sub mu times the forward velocity of the dust sub nu. So here's a surface, and the dust particles are flowing across the surface. They're carrying momentum. So there's a momentum flux across this surface, but the dust particles don't interact at all, so they don't exert any forces on each other. So there are no forces involved here. In particular, the dust on the left side of this surface can't and doesn't exert any force on the dust on the right side of this surface. So this is an example in which the IJ components are purely momentum flux. As another example, let's look at a perfect fluid that's at rest. So remember, the stress energy momentum tensor for a perfect fluid is the mass density times U mu, U nu, plus the pressure times G mu nu plus U mu, U nu over C squared. And now, because the fluid is at rest means that the forward velocity of the fluid matches the forward velocity of the observer. And that tells us then that the spatial basis vectors of the observer are orthogonal to the forward velocity of the fluid. So now let's compute E mu I, T mu nu, E nu J. All of these terms involving U mu and U nu vanish by this result, and we're just left with P times E mu I, G mu nu, E nu J. That, of course, is just Kronecker delta Ij. So in this case, these components of the stress energy momentum tensor are diagonal, and with diagonal values equal to the pressure. So this is just a type of stress. There's no exchange of momentum across any surface because the fluid is at rest. So this is purely stress. It's not momentum flux. Of course, if the fluid is not at rest, if the fluid is flowing, then across any surface there can be a flux of momentum and also forces due to the pressure in the fluid. So in that case, these components of the stress energy momentum tensor would be a combination of momentum flux as well as stress. So again, I think the correct perspective on these components of the stress energy momentum tensor is that sometimes, depending on the context, sometimes it's momentum flux, sometimes a stress, sometimes it can be a mixture of both. But as a matter of terminology, we usually refer to these as the stress components of the stress energy momentum tensor, even if it's a momentum flux. The last thing I'd like to do in this lecture is to talk about the sense in which energy and momentum are conserved. So let's return to the Einstein equations. G mu nu equals 8 pi g over c to the 4th power t mu nu. We have the Einstein tensor on the left, the stress energy momentum tensor on the right. And if you'll recall, the Einstein tensor satisfies the contracted Bianchi identity, which says that the covariant derivative sub mu g mu nu equals 0. So that tells us that the covariant derivative of the stress energy momentum tensor must also vanish. Now, this is an identity. It holds for any stress energy momentum tensor. As long as the equations of motion for the matter field are satisfied. So it's an identity in the sense it's not a restriction on the matter fields or a restriction on the stress energy momentum tensor. Any T mu nu will satisfy this, and you can actually prove that from the variational principle using a Noether's theorem type argument. And I'm not going to go through that argument here, but what I do want to do is explore the consequences of this identity. So let's first consider the simple case of flat space-time. And let's also consider an observer, or actually a fleet of observers. With 4 velocities u mu. So here's our region of space-time, and our observers are traveling along world lines with 4 velocities u, and we'll assume the observers are moving parallel to one another, so they're at rest with respect to each other. And let's use Minkowski coordinates. So that the 4 velocities are just c, 0, 0, 0, 0. And of course we can lower the index using the Minkowski metric. This would be minus c, 0, 0, 0. Now let's take this identity and multiply by u sub nu. So this is del t mu nu times u sub nu. And of course in Minkowski coordinates, this is just an ordinary partial derivative acting on t mu nu. But now the only non-zero component of u is the 0 component. So this is t mu 0 times minus c. But since this is equal to 0, let's just drop the minus c. And we have 0 equals partial mu of t mu 0. And now let's integrate this result over some region of space-time, some space-time volume. So we have 0 equals the integral d4x of partial mu t mu 0. Of course, there's a sum over mu, so let's write that out. This is integral d4x of partial 0 t0 0 plus partial I ti0. Now the d4x is dx0, dx1, dx2, dx3, and dx0 is c times dt. But let me just go ahead and drop the factors of c, set c equal to 1. And let's just write this as dt dx, dy, dz, just for simplicity. Then what we have here is 0 equals integral dt, dx, dy, dz of partial t of t0, 0 plus partial x, t, x0 plus partial y, ty, 0 plus partial z, t, z0. And now this, we can carry out the integral over t since this is a total derivative with respect to t. This is just the integral dx, dy, dz of t0, 0 evaluated at the initial t and the final t. Let's call that t sub I and t sub f for initial and final. And from this term, we have the integral dt, dy, dz of t x0 evaluated at the initial x, or say the left end in x, to the right end in x, and so forth. We have corresponding terms for y and z. Now let's recall the interpretation of the components of the stress energy momentum tensor. This t0, 0 is, of course, t mu nu, u mu, u nu, where these are the four velocities of our fleet of observers. This is the energy density. And similarly, this is the energy flux. Energy flux in the x direction. So what we have here is energy density integrated over a spatial volume, dx, dy, dz. This is the total energy at the final time, tf, minus the total energy at the initial time, ti. And here we have an energy flux and energy per unit time per unit area integrated over time and area. So this is plus the energy lost through the face xr minus the energy gained through the face xl. And then, of course, we have other terms corresponding to energy fluxes through the y and z faces of our space-time volume. So if we put this together, just rewrite these terms, we have the energy at tf is equal to the energy at ti minus the energy lost through the faces. Or through the spatial boundaries. So this is conservation of energy, and we obtained it by integrating partial mu t mu 0 over a space-time volume. And we can do a similar calculation by integrating partial mu t mu I, where I is a spatial index. So we can write 0 equals integral d4x partial mu t mu I, and that gives us momentum conservation. So in other words, it relates the total momentum at the final time to the total momentum at the initial time minus the flux of momentum through the spatial boundaries. So what we found is that in flat space-time, this identity, del mu t mu nu equals 0, implies conservation of energy and momentum. But what about in curved space-time? Well, we can try to repeat the same calculation. We'll start with del mu t mu nu, and we'll multiply it by the vector field that represents the forward velocity of a fleet of observers who are observing these matter fields. And then we integrate this over a space-time volume. So in curved space-time, we have d4x square root of minus g is the volume element. And this is all equal to 0 because del mu t mu nu is equal to 0. So the next step is to bring this u inside the covariant derivative so that we have a total derivative. This is del mu t mu nu u nu, but in order to do that we need to subtract del mu u nu. Now let's simplify this. You might recall from one of the practice problems that anytime you have a covariant divergence of a vector field, so this is a vector field, it's a type 1,0 tensor, there's only one free index mu, and this is like the divergence, but it's a covariant derivative with the indices wired together. Anytime you have this expression, it can be written as partial mu acting on the square root of minus g times t mu nu u nu. Okay, so that's just an identity that you can verify just by writing both of these out. And now for this term, let me go ahead and write another integral sign. We have square root of minus g, and now this is a symmetric tensor, so only the symmetric part of del mu u nu is present here when it's wired together with t mu nu. So we can write this term as 1/2 t mu nu times del mu u nu plus del nu u mu. Now this term integrates to the boundaries, so this term, just like in the flat space case, gives expressions, integrals relating the energy at the final time to the energy at the initial time and the flux of energy through the boundaries. But we also have this term. If you'll recall, this combination is the Lie derivative of the metric g mu nu along the vector field u, and this in general is not equal to 0. If this were equal to 0, then we could interpret this result as energy conservation, but the fact that this term is not 0 is interfering with that interpretation. Also recall that the Lie derivative of the metric is related to spacetime symmetries, so if we have a vector field k for which the Lie derivative along k of g mu nu is equal to 0, then that corresponds to a symmetry. In other words, the space-time is symmetric. Along a translation along the flow lines of k, along the integral curves of k. Along the integral curves of the vector field k. And we refer to k as a Killing vector field. So we can think of the Lie derivative of the metric along a vector field as a measure of how much the spacetime changes as we move along the integral curves of that vector field. So here once again is a picture of our spacetime region. And these are the integral curves of our fleet of observers with 4 velocities u. And we're integrating the identity, the del mu t mu nu equals 0, over a space-time volume. And in general, the space-time is changing as we move along these integral curves. So this is not 0. But if we take, instead of a large space-time volume like this, we take a very small space-time volume. So this is a small space-time volume. Then the Lie derivative along these integral curves is approximately 0. So if we take the volume small enough so that it's small compared to the scale on which the curvature is changing or the geometry is changing, then this Lie derivative is approximately 0. So in that case, we can drop the extra terms involving the Lie derivative of the metric here. So in that case, our identity, del mu t mu nu equals 0, implies the integral over a small volume of partial mu acting on square root of minus g T mu nu U nu is equal or approximately equal to 0. And now this can be integrated to the boundaries of the space-time region to give us energy conservation. But it's usually referred to as local energy conservation because it's only valid in the limit of small volume. Local energy conservation. And likewise, if we replace this vector field u with a space-like vector field, then we could derive a local momentum conservation law. And it would be valid in the limit, again, of small volumes for which the Lie derivative of the metric along that vector field is approximately 0. So in general, in curved space-time, this identity always holds, but its physical interpretation is a little bit less straightforward than it is in flat space-time. It's usually referred to as a local energy and momentum conservation. And you're probably wondering, why aren't energy and momentum conserved globally? Why this restriction to just local approximate energy momentum conservation? And the reason is because in general relativity, the gravitational field can carry energy and momentum. So the energy and momentum of the matter fields, the non-gravitational fields by themselves, should not be conserved, but they're approximately conserved over a space-time region that's sufficiently small for there to be a negligible exchange of energy or momentum between the matter fields and the gravitational field. So this result is only local due to exchange of energy and momentum with the gravitational field.